Okay, before we get into the actual lesson on trends, I just want to take a little review. You guys in class have already done a photoelectron spectroscopy POGL, and so hopefully from that you learned how you can identify elements. And if you just have a periodic table with you, you need to stop the video and grab a periodic table before you begin, because I will be referring to it quite often. So if you look at beryllium, where it's located, you can see that this PES has 2 peaks on it. And now that we understand kind of how this works, remembering that this, that this is the nucleus right here, the 2 peaks represent the 2 different sublevels we have. So this represents the 1s2, 2 electrons, and this represents 2s2. So from a PES, you can get an electron configuration. And sure enough, that is the configuration of beryllium. If you look here, we have a 1s2, a 2s2, that has to be a 2p3. See how these are closer together? Because they're both second energy level. And there's a wider gap here because this is energy level 1. And the difference between is the difference of energy between first and second energy level. So sure enough, that is the electron configuration for, getting ahead of myself, for nitrogen. Let's try this one. This is going to be 1s2. This is 2s2. Whoa, we have, this has got to be a full P, and a 3s1. Again, the number of electrons are indicated here, and they go in order of alpha, that way. So 3s1 would be sodium, right? And sure enough, that's what it is. And here, and I'm just going to number them as I see them. I'm not looking at a periodic table yet. This has to be a 1s2. This is a 2s2 and a 2p6. This is a 3s2 and a 3p6. Now I've got this weird thing. I've got a 1 here, right? And then I've got this 2. So that's probably 4s2. What could this be? Well, it's your 3d1. Why is it first? Well, 3 is, even though it's filled after, it is on the, it is a little bit closer to the nucleus. So if you look, that's why we have that little peak ahead. Now when you write your electron configuration, you can write it in order like this. Even though that's not commonly how we do it. I still believe you need to write it as you've been taught. But if you're looking straight at a PES diagram, your little d, 3d1 here, which is filled first, will come before the 4s2. So 4s2, 3d1, if you look at the periodic table, that is scandium, sure enough. All right, so let's move on to what we're doing today, and that is periodic trends. There's 3 main periodic trends we're going to be looking at: atomic and ionic radius, electronegativity, and ionization energy. Today we're just going to look at this first guy to break up a little bit of this because it gets pretty intense. So a lot of this is based on the law called Coulombs Law, and you might have learned this in physics, and we're going to study it a little more when we get to bonding. But Coulombs Law basically says that the attraction or force between 2 charged particles is equal to the charge divided by the radius. It's proportional to the charge divided by the radius. So the bigger the charge, the greater the attractive force, which makes sense. These Q's represent charge. On your AP sheet, it's Q, capital Q, Q. R squared represents the distance between the 2 points. So today when we're looking at trends, we're actually looking at the distance between the nucleus and the outer electrons. They're oppositely charged, right? So there's going to be that attraction between those 2. And again, it's depend on the charge and the distance. So the bigger the distance between the 2, the smaller the attractive force, which totally makes sense, both in terms of it just makes sense. Things are further apart, they're less attracted, and also mathematically, since that's in the denominator. The use of Coulombs Law is a newer thing to the AP since the redesign a few years back. So the explanation of trends now, in addition to the way we used to teach it, we like to bring Coulombs Law in and get you used to that terminology and verbiage as well. So the first trend we're going to look at is atomic radius. Again, you need a periodic table, so if you don't have one, go get one. Atomic radius will increase as you go down a group. Super simple. Why? Because you are increasing your number of energy levels. The way the AP term that you can use is you can just say shielding increases. What is shielding? Shielding refers to the shielding, literally blocking, that occurs between the nucleus and the most valence of electrons when you have a bunch of energy levels. So the more energy levels you have in between your nucleus and your valence electrons, the more shielding. What does that do? That blocks their attraction. The less attractive, the more spread out the nucleus and the valence electrons are. You can also think about it in terms of Coulombs Law. The distance. As you get further and further down the periodic table, your nucleus is getting further and further from the valence electrons, increasing this distance, right? Which decreases the attractiveness. That makes it a bigger atom because there's less attractiveness. The best way, most efficient way on the AP to say it is you go down the table, shielding increases. Well, what about as you go across the periodic table? Well, as you go across the periodic table, you're not changing numbers of energy levels, so your distance isn't changing theoretically. So Coulombs Law is not really going to work. What's happening, though, is as you go across the periodic table, you're increasing that nuclear charge because you're adding protons without adding an extra energy level. That gives the nucleus more and more and more power, more pull as you move across the periodic table. We call that pull effective nuclear charge. So as you go across the periodic table, you increase your effective nuclear charge, so the size decreases. This is the key phrase on the AP. So to review, as you go down the table, it's shielding. As you go across the table, it's effective nuclear charge. You cannot use those interchangeably. If you use effective nuclear charge when you're going up and down the table, that's incorrect. If you talk about changes in shielding as you go across, that is incorrect. You've got to use the correct terminology in the correct situation. Okay, what about ions? Well, there's a lot of different ways we can look at ions. So I'm just going to give you some examples, and we'll talk about each individual case, and then we'll do some practice problems for both atomic radius and ionic radius. So what happens to the sizes of atoms or ions as we compare them to their own neutral element? For instance, if I'm comparing magnesium +2 to magnesium, whenever you do problems like this, you need to talk about both electrons and protons. The best way and the safest way to do it is talk about that proton to electron ratio. In general, cations are going to be smaller than the neutral atom, than their neutral atom. Neutral. Why is that? Well, if you think about it, when it becomes positive, it loses electrons, right? But that then causes the proton to electron ratio to increase. Increased proton to electron ratio means there's more pull, therefore making the atom smaller or making the particle smaller. Okay, so when you're asked, this is the difference. In pre-AP or in regular chemistry, you just had to say, oh, this one's smaller. You didn't have to say why. Now you have to say why. And you have to talk about the proton to electron ratio every single time. So the reverse is true then if we're talking about anions. The anions are going to be larger than their neutral atom, because you have a decrease in proton to electron ratio. right? Now we have more electrons with the same number of protons pulling on more electrons. Well, that's going to be harder work for the protons, so they cannot pull in as tight. In the first case, when you have more protons than electrons, you have more protons pulling on less electrons, so it's going to be smaller. So you've got to talk about that proton to electron ratio every single time. All right, what about ions in the same family? So what happens if you're comparing something like, if you go down the table and you have F minus 1 compared to Br minus 1 compared to I minus 1? Well, if they're in the same family like that, you just follow the normal trend. If you're going from F to Br to I and they're all minus 1, you just follow the trend and go, oh, okay, as you go down the periodic table, the size increases because our shielding is increasing. Our number of energy levels are increasing as well. What about, and it's the same thing for positives. So if you have like Ba plus 2, Sr plus 2, and Mg plus 2, I'm going sneaky there. That's actually going up the periodic table. So these are decreasing in size, because that's going up the table. So if they're in the same family, then you're cool to follow the trend. But where you have to really be careful is in a problem where you have different charges of different ions. You're like, what am I going to do? What do I mean by that? What if I asked you to compare Ca plus 2 to S minus 2 to Ar? There's going to be some steps. Whenever you have, these are not in the same family, like calcium plus 2, calcium's on the left side of the table, sulfur's on the right side of the table. How am I going to compare their size? You really can't just look at it unless they're in the same family. You can't. You have to figure out, first off, what are they all isoelectronic to? So take a look at calcium plus 2. Calcium, where it normally is 4s2, if it were to become plus 2, it would lose 2 electrons and become isoelectronic to argon. Sulfur, minus 2, if you add 2 electrons to sulfur, it's also isoelectronic to argon. And then we're comparing argon in the mix. So all of these are isoelectronic. Whenever you have isoelectronic, you need to compare basically the one with the more protons. Isoelectronic means the same number of electrons. So the one with more protons then is going to pull in and make the smallest atom. Looking at the charge, you're capable of figuring out which one has more protons, or you can just look at the periodic table and figure out which one has more protons. So if you're looking at this, when you're answering this, you need to talk about, again, this is very, very important. You need to mention both protons and electrons. You always, just like I mentioned up here, protons and electrons both have to be referred to. So we would say something like, since these all have the same number of electrons, the one with more protons has the smallest radius. Well, which one has the most protons? Well, like I said, you can look at the periodic table and see, okay, well, calcium plus 2 is 20. Well, calcium, not plus 2, just any calcium, plus 2 or not plus 2, has 20 protons, and sulfur only has 16. Or the charge kind of tells you that, right? If all of these has the same number of electrons, the one with the most positive would have a higher proton to electron ratio than the one with the least. So if I were ranking these from small to large, I would go from my positive all the way through to my negative ion. You have to mention electrons and protons in your answer. That is not optional, okay? Because a lot of students will say, oh, calcium has more protons, or calcium has a plus 2 charge. Well, what if I'm comparing calcium plus 2 to iodine negative 1? Well, that won't work because iodine has got a lot more shielding than that calcium. So you've got to mention both. All right, and finally, we're going to do some practice with all of this now and see how you do. It says rank the atomic sizes of the following elements. So we're comparing O to N to Ne. Well, if you look, those are all in the same energy level going across. So I know that as we go across, we get smaller because of the effective nuclear charge. So I want to go from small, according to the question, they want you to go from small to large. So my smallest is neon, then my next is oxygen, and then my next is nitrogen. All right, rank the atomic sizes of the following elements from small to large. What are we comparing here? Looks to me like calcium, potassium, and rubidium. So we're almost comparing things in the same family, but not really. Size, and one thing that you do need to know is level takes precedence. So because rubidium is on the next level down with more shielding, it's definitely going to be the largest, okay? And then between the two then, you can compare potassium and calcium because you already know that as you go across it gets smaller. So calcium would be the smaller one, and then potassium would be the one in the middle. Okay, next one. Rank the ionic sizes from small to large. Now, if you notice, these are all kind of all over the place, right? I can't just look at the trend. I can't just look at the family. I need to find out if any of these are isoelectronic to each other. So sodium +1 is isoelectronic to neon, and magnesium +2 is isoelectronic to neon. Sulfur -2 is isoelectronic to argon, and chlorine -1 is isoelectronic to argon. So looking at this, I know that these two are going to be smaller than those two, right? Because I know neon is smaller than argon because of shielding. So let's just look at the two that are isoelectronic to neon. Which one has a bigger nuclear charge? Magnesium, +2. That's going to be, because it's +2, it means it's got 2 more protons than electrons. Now, these both have the same number of electrons, so that means magnesium has to have more protons than sodium. So that's going to be my smallest, and then sodium is going to be my next. So now in the ranking, I can look at my argon, and my argon guys, again, I'm looking at the one with more protons. Since they have the same number of electrons, the one with the smaller charge, smaller as in less negative, is going to be the one that's going to have a bigger nuclear pull. Or I can look at the table and see that chlorine has 17 protons and sulfur only has 16. So chlorine is going to have a stronger nuclear pull than sulfur. Okay, so the trick again is to figure out what they're isoelectronic to and go from there. So now let's just quickly finish these up. Circle the larger particle in each of the following. All right, if we've got neutral atom and its cation, same number of protons, but that Fe+3 has less electrons to pull on, so it's going to be smaller. So that's the bigger one. I know the one here, they both have the same number of protons, As, but the one with the more electrons is going to be larger because that's more stuff for those protons to pull on. So here, negative is larger, and here, neutral is larger. Circle the larger particle. Here we got to, again, see what they're isoelectronic to. This is isoelectronic to argon. Both of those are. So which one is larger? Well, the one that has less of a nuclear pull. That guy. These are both isoelectronic to krypton. So which one is larger? That one. All right, bromine is isoelectronic to krypton, and xenon, Cs+1 is isoelectronic to xenon. Well, now I just rank those based on their size. Xenon is way bigger than krypton, so xenon is the larger one. And here I have something isoelectronic to helium and something isoelectronic to neon. Which one is it? Do you see how I can't use the charge here? Like, I'll show you. This one, the charge does kind of work out. That's larger. But like in this example, normally I'd say something with a -1 is larger than something with a +1. Well, not in this case, because xenon has more shielding than krypton. So you've got to look at what they're isoelectronic to. Okay, go do your homework.